All right, let's get going with a lecture on normal distributions and z-scores. So we'll see a couple of things from past lectures pop back up here. Um, One of them will be histograms and frequency distributions. We'll also see standard deviation come into play. Let's go ahead and start off with those frequency distributions, and let's actually look at a set of data here. So we've seen this highest recorded temperature in each state table. We've seen this before a couple times. And we've got all of this data here, and this just seems like a big blob of data, but it turns out that if we actually make a frequency distribution and then a histogram for it, it actually looks pretty interesting. So let's go ahead and recall ourselves doing that. So we made a frequency distribution. We decided to do 7 intervals here, and by looking at the low temperature of 100 and the high of 134, we said, all right, if we want to have 7 intervals, if we want to have 7 groups, we should split them in groups of 4. So 100 to 104, 105 to 109, and so on. And then all we did is we just went through the data and we just said, all right, there's 3 states that fall under this category of this temperature. There's 8 that fall in between 105 and 109, 16, 13, 7, 2, 1. And we've got all those there. This is our frequency distribution. Well, what we did after this was we actually plotted this on a histogram. So we had our histogram here, and we say, hey, look, in between 100 and 104, right up to that limit, not quite at 105, but 100 to 104, there's 3 right there. And then 105 to 109 is that 8. That's what that was right there. And then we kept going on, and we had all the rest of the data points there. So this is our histogram, and what we pointed out very briefly, we didn't really talk about it, but what we pointed out was the shape here. We said, hey, take a look at this shape. To me, that looks interesting. It almost looks kind of like a bell. And this shape is actually very common. With almost any data, and keep in mind that word almost, with almost any data, it tends to look like this. If you plot a histogram of exam scores, if you plot a histogram of the height of people, if you plot a histogram of the highest temperature ever recorded in each state, it tends to look like this. And not all data does, but most happens to. So this sort of shape here, we actually decide to give it a name, and we call this shape, informally, we'll call it a bell curve. Formally, we'll call it a normal distribution. And so when we say normal distribution, what we're actually referring to is a set of data. So if I give you the set of data that is the highest recorded temperatures in each state, if I tell you that that is a normal distribution, I'm referring to all of that data. So what I might say verbally to someone who I'm having a conversation with, I might look at this table and say, oh yeah, this table, this data right here, this data is normally distributed. And so that normally distributed is a name for data. And what we say is it follows this shape if you were to plot it on a histogram. But this actually means a couple things. If we're looking at a histogram, we're recognizing, and let's go ahead and put in a little histogram in here. Maybe it looks something like this. So let's say we have a histogram, just similarly to what we had last time with the states. I'm just kind of guessing and estimating and putting something in there. Maybe we have a histogram that looks like that. And so we kind of put this curve to it and we say, great, that's what it looks like. Hey, this looks like a bell curve. It looks normally distributed. So what we notice here is that for this histogram, these sets of values, and we could even go back here and we could say, hey, look, these sets of values, the temperatures in between 110 and 114, those appear the most often. And so what actually happens with a normal distribution is not only do these appear the most often in this particular range, but they tend to be the mean as well. And so the big thing here with normal distributions, as we're going to see, if something is a perfect normal distribution, if it perfectly follows this shape, then we'll actually see that the mean and the mode are actually the same. We'll also see that it's the same as the median, but we'll get to that in a second. So what we're seeing here is that for this data set, this frequency distribution, the mode is clearly 110 to 114. Notice I'm not being specific. I'm just talking about the mode in terms of which interval. But if we're talking about the mode with respect to intervals, this interval is the mode. Well, it turns out that because this data is normally distributed, it also works out that the mean kind of falls somewhere in this range right in here as well. And so if we have something that's a normally distributed set of data, we know that the values tend to be near the mean. They tend to be near the average. You can think about that like an exam score. If I tell you the average on an exam was 76, if you were to actually pool everyone's test scores together, most of them are near 76. There's obviously some higher, there's obviously some lower, but they tend to be near 76. Now, talking about this idea of some of those test scores being higher and lower than that average of 76, what also happens with the normal distribution is we tend to have symmetry. And what that means is that we tend to have roughly the same number of people score higher than the average and roughly the same number of people score lower than the average. You could actually look at this here on this data set here. If you were to calculate the exact mean, the exact average of all of this data, and you were to count how many data points are above it and how many data points are below that average, you'd get roughly the same number there. And I would encourage you to do that on your own time. You can kind of see it here. If the average is somewhere in this range right here, this maybe 113, 114, 115 range, you can kind of count. You could say, hey, well, there's 3 here, there's 8 here, there was 2 and 1 over here. I think this was 13 and 16 and 7. You know, we have all those numbers. You could kind of add all those up, and you could say, well, yeah, it's roughly the same number of data points on either side of this mean that we have. And it turns out that that's actually roughly true. So normally distributed set of data, a lot of explanation there, but the two biggest things are that the values tend to be near the average and they tend to be symmetrical about the average. Just think with an exam. If the average is a 76, pretty much everybody scored around 76. There were some higher and some lower, but it tends to work itself out so that everybody is around 76, and typically an equal number of people score above and below that value of that 76 that I'm making up. So if we have something that is perfectly normally distributed, and when I say that, I mean it follows this curve. Oops, let's erase that, all of that. If something is perfectly normally distributed, it follows this curve exactly. This is a shape. There is an actual function that describes the shape here. If I have a perfectly normally distributed set of data, then we have a couple properties. The value in the middle of the distribution, which happens to appear most often, for that I'm referring to this value right there, that value, that is the mean. And it also happens to be the mode. Also, another property is that the distribution is symmetric. And you can see that. If it perfectly follows this, I mean, you can see this line of symmetry right there. It's perfectly symmetric. My histogram, if there was a histogram lying underneath this that we were kind of hiding, it would be perfectly symmetric, right, like that. And so what that actually tells us is that if we have a perfectly symmetric set of data, then the median is also right in the middle. And it also happens to be the mode and the mean. And so that's what we're seeing down here. The mean, median, and mode are always the same if you have a perfectly normal distribution. The last thing that we're going to talk about is area here. And this is kind of just a prelude to what we'll get into more later. And the area underneath a portion of the curve tells you the percentage of data values that fall between the values that start and end that region. That is a lot. Let's go ahead and take a look at this a little bit more carefully. So for now, what we're going to do is we're going to follow what we're going to call the empirical rule. You'll also hear this, well, actually, you'll primarily hear this called the 68, 95, 99 rule. And you can see that right there. So there's a lot of colors, a lot of numbers, a lot of shapes, and a lot of letters going on here. So let's kind of break this down. just for some labeling, we'll have the following here. Mu is the mean. Sigma, let's go ahead and label that one. Sigma is standard deviation. So this little guy is a sigma. And then we won't worry about probability density. Don't worry about any of that over there. So what we've got here is we've got this normal distribution. And you would make this, if I gave you a set of data, you would plot a histogram on it. And you would say, oh, look, my histogram kind of follows this shape. Well, what we're saying here is that if it perfectly follows the shape, which it won't ever perfectly follow it, but it'll end up being pretty close. But if it perfectly follows this shape, then what we can say is we can basically take this underlying histogram that we have, build it up, and we could say, all right, if we started counting data points and we started saying, okay, I've got my data points. Most of them are around the mean right here. You can see it appears the most often. Remember, this is a histogram. And so the y-axis is talking about how many of those data points we actually see. So the mean is right here. It also happens to appear the most often. And what we've got is that if we move a standard deviation away from the mean, so you notice we'll have to calculate standard deviation here. But if we move a standard deviation away from the mean in either direction, what that means is that 68% of your data lies in this region, in between here. We're going to do an example of this in a second, so don't worry if this is confusing. But basically what we're saying here is that if you have an average, maybe let's say you have an exam where the average is 70, and the standard deviation, we go through, we calculate it just like we know how to, and we get the standard deviation is 10. Well, what we're saying there is that, let's actually go ahead and write this up. So what we're saying, if we have an average of 70%, let's just say a 70, just a score of 70 on an exam, and we calculate the standard deviation as being 10. What this graph right here shows us, this red region in here in the middle, that tells us that if I take my 70 and I go plus 10 and I go minus 10 so that I have 60 and 80, what this graph tells us, it tells us that 68.27% of students scored between 60 points and 80 points. And this is wonderful. This is great. And the reason this is great is because not only are we using standard deviation to tell us how spread out our data is, right? We're using this value of 10 to actually tell us, oh, I now have a sense of how spread out my data is because I know the percentage. I know the percentage of students that scored between these two scores. When I'm looking at this, I'm saying, hey, 68.27%, that's a little bit higher than 2/3. So if I'm looking at this, if I'm looking at a set of exam scores and I see this, I write this down, I say, hey, 2/3 of the class was between a 60 and an 80. Great. Now I have an idea of where people scored just in general, and I kind of know how spread out my exam was. If my standard deviation was different, if my standard deviation was 1 instead, then I would know that 68.27% of students, a little bit more than 2/3 of the class, scored between a 69 and a 71. And so that tells me it's really tightly packed. And so we're seeing exactly what we talked about before, with standard deviation being a measure of variation. And now we're actually turning it into a way of talking about what percentage of your data falls in between 2 points. And so if we were to keep going here, we could go another 10 down and another 10 up, and I'd end up at 90 and 50. And the information that we have now is that 95% You'll notice that's this red and blue region. It's all of this in here. You'll notice that I'm going 2 standard deviations away from the mean. I'm starting at the mean and I'm adding 2 sigma. I'm adding 2 standard deviations there. And then I'm subtracting it there. So I'm moving 2 away, and you can see me doing that right there. So the result that we have is 95.45% of students scored between 50 and 90. And now I'm looking at this and I'm saying, all right, 95%, basically everybody, almost the entire class scored between a 50 and a 90. That tells me how spread out my data is. That tells me that I don't really have many students. I've only got about 5%, 4.5% of my students scoring outside of a 50 or a 90. So there wasn't really very many people above 90 and there wasn't very many people below 50. And that's what that's telling me right there. And then we could even go one more step further and we could go another 10 up to 100, and we could even go another minus 10 down to 40. And the last thing that we're going to see here is this 99.73. You can see I go 3 sigma. I'm including all of these colors here, red, blue, and green. So I go 3 standard deviations away from the mean. That encompasses 99.73% of my data, 99.73% of the students that took this exam. And so what we're seeing here is basically this normal distribution is just allowing us to basically have a fancy way of counting our histogram. Rather than looking at a histogram like this and saying, all right, let's just count. Okay, we've got 16 here. So let's look to the left of this 16. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And oh, we've got 11 to the left of this. And then we've got 23 to the right of it. Rather than doing something like that, we actually have a very formal way of saying, all right, we actually know how much of the data is exactly stuck between certain points. And so we're doing that right here with this average. Let's go ahead and do another example here. Let's say that we're talking about people's height in inches, and the average height in inches, roughly 68. Let's just say that. If I'm actually remembering correctly, that I believe that's the average height of a male in the United States, 68 inches. So that's the average. I don't actually know the standard deviation off the top of my head. I'm going to make something up. Let's say that the standard deviation is equal to 5.5 inches. So we got an average height and we have a standard deviation. What this graph tells us right here, it says if we move 1 standard deviation above the mean and 1 standard deviation below the mean, mark down those heights, and then ask ourselves how many people are in between those heights, it's 68.27% of the population. And so looking at this, we would say, all right, let's start at 68. Let's go plus 5.5 and let's go minus 5.5. So if we add 5 to this, we're going to get 73.5. And if we subtract 5, we're going to get 62.5. And so what we're saying here, we're going to mark these down. We're going to say, all right, we've got those right there. So now we can say that 68.27% of males, I guess, because we're talking about the average height of a male, would be have a height between 62.5 inches and 73.5 inches. Now, don't take this perfectly because I made up this standard deviation here. But This is the piece of info that based on this made up standard deviation. That's what we have. We now know that a little bit more than 2/3 of males have a height between 62.5 inches and 73.5 inches. And so that tells us right there exactly what percentage of males have that height between these in this range. You could do this even in another way. We could go back and we could look at this symmetric distribution here. And you could say, all right, let's ask the question. We said the average height of a male was 68 inches. How many males are higher than that? Have a height higher than 68? How many males are taller than 68 inches? Probably naturally, you just think, oh, well, if 68 is the average, then half are above and half are below. And that's exactly what this normal distribution says. Because this is perfectly symmetrical, exactly half are above the average and exactly half are below the average. And so if I asked you, hey, what percentage of males had a height higher than 68 inches, taller than 68 inches, you would say half of them. Well, now I'm just asking, hey, what percentage of males are in between this range? And you're using this figure here, this graph, to tell me that it's 68.27. So we've come up with a great way to talk about the spread of data. We've come up with a great way to actually say, all right, this is the percentage of people that fall in these widths, in this interval, in this range of, 1 standard deviation above and below, or maybe 2 standard deviations above and below, or maybe even 3 above and below. And so now that we have these percentages, what I want to make note of is when this is pretty useless. Well, what if I asked you, hey, what percentage of people scored in between 65 and 75? Well, now doing our, sort of jumping by standard deviation, there's no way to get to 65 or 75. There's just no way to do it. Maybe you could go half a standard deviation, but that doesn't help us because this graph doesn't tell us that stuff. It doesn't tell us what happens when we go half a standard deviation away. It doesn't tell us how much this portion, it doesn't tell us how much that is right there. And so this is pretty limited, but in the scenario where you're specifically asked about the interval of 1 standard deviation or 2 standard deviations or 3 standard deviations, then you can answer using these figures here. So let's continue on. We're going to look at the idea of a z-score. And what a z-score is, it tells you how far away a data value is from the mean. And so if I'm looking at these test scores here, and I say, all right, I want to know how far away is 50 from my average of 70. Well, there's a couple of different things you could say. You could say it's 20 away. And that's helpful because now you know that, here we were talking about exam scores. And so you know that the person who scored a 50 is 20 points away from the average. But what I think is a bit more useful is to say that 50 is 2 standard deviations below the average. That now tells me how far away that 50 score is in terms of the standard deviation. And that gives me a very normalized way, a very set standardized way that I can talk about where a data point is. Now that I'm using that notation, that jargon for, hey, this 50 is 2 standard deviations away from 70, I can say, hey, 80 is just 1 standard deviation above it. 100 is 3 standard deviations above it. Oh, where's 85? Well, 85 is 1.5 standard deviations above it. And so we now have a way of saying where these data points are relative to standard deviation. Well, how we calculate it is we just take the data point that we're curious about, we subtract off the mean, and we divide it by S, the standard deviation. And this is exactly what we would have done in our heads. If we said, we just said, all right, let's look at that average of 70. And if we want to know where that 50 data point lies, if we want to know its z-score, we're going to do 50 minus 70 divided by that standard deviation of 10. Well, this ends up giving me -2. And that -2 tells me that the data point is 2 standard deviations below the mean. The negative tells me below. If it were positive, it would tell me above. So just straight by this calculation here, we're exactly telling the reader or whoever's doing this problem, we're telling them, hey, 50 is 2 standard deviations below the mean of 70. If I asked you about, hey, let's say I had a data point that was 73. Well, okay, let's subtract that from the mean, subtract the mean from that, divide it by 10. You're going to notice you get 3 over 10 here, which is equal to 0.3. And so what this tells me is that a data point, someone who scored a 73, they were 0.3 standard deviations above the mean right there. And so there's a z-score calculation for 73. Now, you've been looking at this slide for a bit. What you might notice is that standard deviation is S right here, but yet before we had sigma notating it. There is a reason for that. I'm not going to get into it. There are slight differences in standard deviation calculations. Really what it boils down to is when we saw last time talking about standard deviations, we divided by n-1. Some people divide by n. So that leads us to kind of 2 slightly different versions of a standard deviation. For our purposes, we're not really going to focus on that. We're just going to gloss over it. Let's say that we're going to use S moving forward. We're going to continue using S as a notation for standard deviation. Here we use sigma just because I pulled this graph from the internet. So we've got S for z-score or for standard deviations. We've got Z for z-scores, and we realize that a z-score is a measure of how many standard deviations we are away from the mean. So let's do an example. Let's say that Jim scored an 87% on his last exam, and the average was a 73.5, and the standard deviation is 4.5. If we want to know Jim's z-score, there's 2 ways that we can calculate this. The first thing that we could do is we could use our formula. We could say, all right, we've got his score of 87. We have the average of 73.5, and we have the standard deviation of 4.5. So take that difference, divide it by the standard deviation, you get 3. So what this tells us is that his z-score is 3, but more importantly, it tells us that he scored 3 standard deviations above the average. This would be very good. On an exam, if you were to like curve an exam or something like that, this would definitely be considered an A. 3 standard deviations is pretty hard to do. And the reason we actually know that is because we can go back to this graph right here and we can recognize that if I go 3 standard deviations away from the mean, I'm encompassing 99.73% of the data. Basically, all of it, almost all of it. So what that means is that the remaining 0.27% is outside of this region right here, meaning that it's greater or less than 3 standard deviations away. So it's saying it's really hard to do that. So if someone scores 3 standard deviations higher than the average, that's really tough to do. It means that they are outside of this 99.73%. That means that they're in a class of 0.27% of people that scored higher than or lower than 3 standard deviations. So they either did really good or really, really bad. So 3 standard deviations is tough to do. Jim did it here. And so the other way that we could calculate this, so we've got our z-score here, we could just do it manually. We could say, all right, he started at 73.5. What if we just added 4.5? Great. Now we've added S. Okay, what if we add another 4.5? Well, at this point, we've added another S. Well, if we add 4.5 again and we add another S, you'll notice here that I'm adding 3 S's. Oh, so you're telling me he's 3 standard deviations above the mean. So his z-score is equal to 3. and you just calculated that manually right there. Now, this manual way won't always work. What if we didn't exactly get his score when we counted our way up? Well, then that's where this formula comes into play. So we've talked about normal distributions. We've seen that they are symmetric and that they're nice, that their mean occurs the most often. Mean equals median equals mode. We should understand, hopefully, that not all data, or actually data is never perfectly normally distributed, but it's usually pretty darn close. And we even saw that on our first histogram back here. It doesn't look perfect, but it looks pretty close to this bell curve shape. And so we've used that to talk about z-scores and standard deviations, and we'll continue on with this in the future, still looking at all this stuff. But for now, that'll go ahead and be the lecture.